Hey there, chemistry students. This is Miss Ruark. This is podcast 7.1, where we're going to talk about the kinetic molecular theory and pressure and how to do pressure conversions. Okay, so kinetic molecular theory is talking about kinetic energy of molecules. So kinetic energy is the energy that's due to motion. You have kinetic energy and you have potential energy. Potential energy is stored or energy that has the potential to move, whereas kinetic energy is the energy that's due to that motion of the molecules. Okay? All matter consists of things that are in constant motion. We call those atoms, molecules. Right? If we add kinetic energy or we add more energy to those molecules, they're going to move rapidly and the object will begin to expand. Okay? So think, when you have a helium balloon, if you have it inside your car and inside your car you have the air conditioning on, when you get out of your car and it's on a warm day, when you get out of your car, the balloon expands. And the reason the balloon expands is because the gases inside of it are being heated up by the air. And when the gas molecules get heated up, they move faster and they're going to move more further apart. And so that's what expands that balloon out. Well, if you lose kinetic energy, the molecules and the atoms are going to slow down and the object will start to contract and come in on itself. And so that would be if you take that balloon on a nice hot day and you put it inside a nice cold room. Well, the molecules will slow down. When the molecules slow down, they stop moving out so far they come closer and closer to each other, and that's why the object gets smaller. All right, so to add or lose kinetic energy, the way we do that is by adjusting the temperature. If we add heat, we add temperature, or we add energy. Okay, and what is temperature? Well, temperature is just the measure of kinetic energy. So the more kinetic energy you have, the higher the temperature. Additional kinetic energy is going to cause those atoms and molecules to collide more often, which is going to increase your pressure. Okay, so that's kind of the same thing that happens inside of this hot air balloon here. Inside that hot air balloon, if they want that hot air balloon to go up, they have these little burners in here and they pull the cord and the cord allows the flame to come up, and when the flame comes up it heats the gases inside. When it heats the gases inside, they expand, and that's what allows the balloon to take the people inside of it up and into the air. Well, it also has these valves up here. These valves up here on the top are going to allow that hot air to escape at a controlled rate if you want to go down or descent. Okay, so gas laws right there. Okay. Pressure. Pressure is the force per area of an object. Okay. Gases, guess what? Gases have pressure. Gases are made of atoms. Atoms have pressure. Okay. So the gas pressure is going to be the force that's caused by collisions of these gas particles. Okay, they could be collisions with each other, they could be collisions with the container. All right, and a vacuum, and I know you've probably heard of this. Now the vacuum I'm speaking about is not a Hoover vacuum. It's not the one that you go home and clean your floor with. No, this vacuum is something that you can take out all air. So you kind of suck the air out of it. So it's just empty space. There's no particles, there's no pressure. Okay? And gases are compressible. Well, compressibility just measures how much of the volume of a substance can decrease under pressure. All right, so let's think about gas particles. Gases can be compressed. A marshmallow. A marshmallow has a lot of air in it. And gas particles, they're moving really fast, but guess what? There's a lot of space in between them, and there's all that space, you can squeeze those particles together. And that's why a marshmallow, you can squeeze it down a lot because there's so much air in between it. Okay, so you're squeezing those gas particles together. They're easily compressed, easily squeezed into a smaller volume. Okay, that's what the gas pressure is all about. So atmospheric pressure, well, guess what? It's from collisions of particles in the air. Okay, the air all around you has a mass. It lays on top of you, and it does exert a pressure. The pressure that you feel, the pressure that it's exerted on us, is called the atmospheric pressure. Now, you hear a lot about atmospheric pressure in the morning when you watch the news. On the weather, they talk about barometric pressure. Okay, what they're talking about is millimeters mercury is the unit that they measure in, and it's just talking about how much the air pressure, this is an example of a barometer, this picture here, and there would be mercury here in this little container, and mercury that goes up the column. If there's a higher air pressure, which means you have more air particles pushing down on the mercury in the column rises, and that shows an increase in atmospheric pressure. If there's less particles pushing, then the mercury here rises, and it would lower here, and then the atmospheric pressure would be lower. Okay. Higher elevations. Okay, sometimes when you go into higher elevations, they have on the back of a box, like you're going to make brownies or something. On the back of that box, they have ingredients, or they have directions for just anybody to cook, and then they also have a degree. I can't talk. Sorry. They also have instructions for how to bake at higher elevations. You'll notice that you use a lower temperature, and that's because at a higher elevation you have fewer air particles. Fewer air particles means that there's not as much pressure pushing down on you, and if there's less pressure, then you use less temperature. And that's what we're going to be learning through the gas laws, is how that pressure affects the temperature, etc. All right, in a liquid, you have what we call vapor pressure. Now, vapor pressure is when the molecules inside of the liquid here, these molecules in the liquid are trying to, well, they're not trying to, but every once in a while they're going to come up and they're going to evaporate into a gas. Okay, so they'll come up and evaporate into a gas. And when they come up and evaporate into a gas, you've got all these gas particles that kind of sit here above the liquid. Okay, that's where your vapor pressure comes from. That's your vapor pressure. It's all this gas particles that's sitting right here above your liquid. Okay, at a higher temperature, you're going to have a higher vapor pressure because you're going to have more molecules that are going to have a higher average kinetic energy, and they're going to be going back. They're going to be escaping out quicker. At a lower temperature, you're going to have a lower vapor pressure because those molecules, again, have a lower average kinetic energy. And when we measure air pressure, common units would be Pascal, which are PA, and then we also have atmospheres. Okay, and atmospheres would be ATMs. ATM does not stand for atom, it stands for atmospheres. Okay, you can also see kilopascals, kPa. Those are just some of the ones, and then of course millimeter mercury would be another one that you would see from the barometer, right? But the ones you'll see the most would be pascals, kilopascals, and atmospheres. All right, so units for pressure. So here are some units. We have atmospheres, ATM. We have torricellis, which we say are torrs. It's named after an Italian physicist, Torricelli. And then millimeters of mercury. Millimeters of mercury would be mmHg. And then pressure conversions for these. Well, one atmosphere, oh, and I also talked about pascals. I don't know why these aren't on here. Pascals, which are PA. And then kilopascals, kPa. Okay, so one atmosphere is equal to 760 millimeters mercury, which is equal to 760 torricelli. I wonder if I have these written here. No, I don't. Okay. All right. And that would be equal to 101.325 pascals, which is the same thing as 101.325 kilopascals. Okay, so get familiar with these. They are going to be your best friend through this unit because you'll have to do a lot of pressure conversions. Okay, speaking of pressure conversions, here's one that we can try together real quick. It says, what is the pressure? So we're looking for pressure of 450 kilopascals in ATMs. So we need to go from 450 kPas to ATMs. And then they want us to go to mmHgs. All right, well, you have it written on your paper. We know that one atmosphere is equal to 101.325 kilopascals, which is also equal to 760 millimeters mercury. Okay, so we're going to use those conversion factors to get there. So we set it up 450 kPa, multiply it by a fraction. kPa comes on the bottom because that's what we want to get rid of. And we know that kPas and atmospheres are directly related. We know that one atmosphere is equal to 101.325 kPa. Right, kPas cancel and we're left with atmospheres. So now we'll just solve. Let me get my calculator. All right, so, oops, went too far. All right, 450 times 1 divided by 101.325, and the calculator gives us 4.325. 4.4411547 ATM. How many significant figures do we want? 2 significant figures. The 0 is a trailing 0, right? So 4.4 does not change atmospheres. All right, well, they don't want us to stop there. They said we want to know what is that in millimeters mercury. So keep this number, this long number here if you can, and use it. We know that 1 atmosphere is equal to 760 millimeters mercury. And we just keep going. That way we can get an accurate number. If you use this one here, your number is going to be rounded. It's not going to be very accurate. All right, so we take that number and we multiply it by 760. And we get a really big number, 3,375.27757. All right, 2 significant figures. The 7 makes the 3 go up, so this should, if this is in the thousands, it has to stay in the thousands. So 3,400 millimeters mercury. That's a lot. That's a lot of pressure right there. All right, so that gives you an example of how to do these. So now you'll be able to do your pressure conversion worksheet, and I'll see you in class.